Throughout this lesson, we're going to look at thunderstorms. They are very important weather events generally, but are particularly significant to aviation because of the hazards that result from them. Well-developed cumulonimbus clouds are required for thunderstorms, but the occurrence of a thunderstorm is most likely when the following criteria are met: a lapse rate greater than the saturated adiabatic lapse rate extending to well above the freezing level, sufficient water vapour to form and maintain the cloud, and a trigger action to produce the ascent of the air and cloud formation. The main trigger actions that cause air to ascend and form vigorous convective activity are convection from surface heating, orographic uplift, convergence, and frontal uplift. There are generally two different types of thunderstorms: ones that occur in a single air mass, most common in summer and occasionally spring or autumn months, and frontal thunderstorms, which are the more common type in winter. Let's take a look at these in a little more detail. In non-winter months, thunderstorms can be caused by convection, convergence, or orographic uplift. These air mass or heat-type thunderstorms are most frequent over land and generally form by day, although of course they can linger through the evening and on occasions well into the night. In warm air masses they tend to form in very slack pressure systems, such as coals or weak lows. In colder, polar air, they are usually found in the deeply unstable air well behind a cold front. Although mainly isolated, this type of thunderstorm does on occasions form in organized lines or large groups, which we will discuss later. Thunderstorms also occur on cold fronts, or very occasionally on occlusions. In these cases, they are often embedded in layered cloud, which makes them particularly hazardous to aviation. They form over land and sea and are the most common type in winter months. Frontal thunderstorms are associated with active fronts, and it's not unusual to encounter line squalls underneath the embedded cumulonimbus clouds. Let's look at the way heat or air mass type thunderstorms develop. There are three stages we can identify: initial stage, mature stage, dissipating stage. The initial stage is characterized by the growth of cumulus clouds both horizontally and vertically. Strong updrafts produce clouds of great vertical extent. Air is drawn into the cloud from beneath and the sides. This stage usually lasts for around 20 minutes and produces a cloud sometimes 5 nautical miles across. The mature stage is when the cumulonimbus has formed and precipitation occurs. This stage usually lasts for a further 20 minutes. Rain, hail or snow can be produced, and as these fall, strong downdrafts are produced of up to 2,000 feet per minute, bringing cold air down to lower levels within and below the cloud. These downdrafts only warm out at the saturated adiabatic lapse rate, and are therefore frequently colder than the surrounding air beneath the cloud. This contrast causes the air to sink at a faster rate. As the precipitation in the downdraft descends, some of the precipitation evaporates. This phase change needs latent heat, and so heat is removed from the surrounding air. This process again increases the temperature contrast between the downdraft and the surrounding air, causing the cold descending air to sink even more quickly. The upcurrents within the cloud can reach 10,000 feet per minute, and as the cloud top rises by as much as 5,000 feet per minute, the cumulonimbus will just begin to develop the characteristic fibrous anvil top. The rising and falling water droplets, hail and snow produce a build-up of static electricity. The top of the cloud becomes positively charged, and the lower part negatively charged. The build-up eventually leads to lightning discharge and thunder. The mature stage usually lasts for around 20 minutes, and some of the characteristics associated with this stage are gust fronts, microbursts, macrobursts, and perhaps tornadoes. As the descending air pours out beneath the cumulonimbus cloud, it hits the ground and spreads out in many directions. Where this outflow supports the low-level winds, we get a noticeable gust front. This stretches out in advance of the cloud and can sometimes be over 15 nautical miles, or 25 to 30 kilometers, ahead, with a depth of up to 6,000 feet. Microbursts are the concentrated downdrafts under the convective cell. These are usually very strong, but restricted to within 3 nautical miles, or 5 kilometers of the cloud. Macrobursts are similar, but are larger, extending out to as much as 5 nautical miles, or 7 kilometers, away from the cloud. Micro and macrobursts are usually accompanied by precipitation, and their presence can be noted. But on occasions the strong downdraft is dry, making them far more difficult to spot. The dissipating stage of a cumulonimbus starts as the anvil top becomes fully formed. Precipitation at this stage is usually heavy, with severe turbulence in and around the cloud, and severe icing in the cloud itself. Lightning and thunder are still likely at this stage, which may last for between 1.5 and 2.5 hours. So far, we've looked at individual storm cells, which, on average, last from start to finish from around 2 to 3 hours. Once developed, these types of storms move in the same direction as the winds at around 10,000 feet. These individual thunderstorms, although on occasions quite large, don't last any longer because the downdrafts caused by the precipitation suppress the upcurrents necessary to maintain the cloud. The two effects therefore cancel each other out. There is, however, a scenario whereby a feedback mechanism can exist, which changes things dramatically.